Imagine the night sky ablaze with a light brighter than billions of suns. This, my friends, is the spectacle of a supernova, a celestial event so powerful it outshines entire galaxies for a brief, glorious moment. These cosmic fireworks are not just visually stunning, they are fundamental to our understanding of the universe. Join me, fellow stargazers, as we unravel the mysteries of supernovae and hypernovae, revealing the secrets they hold about the universe's past, present, and future. Supernovae and hypernovae are cosmic lighthouses that illuminate the distant reaches of the universe. Their intense brightness allows astronomers to observe them from billions of light-years away, providing valuable data about the cosmos. These stellar explosions act as cosmic laboratories, allowing scientists to study extreme physics unattainable on Earth. Without supernovae and hypernovae, our own solar system, with its abundance of heavy elements, would not exist. The study of supernovae and hypernovae reveals the dramatic processes that unfold when massive stars exhaust their nuclear fuel. By deciphering the light curves, spectra, and remnants of these explosions, astronomers piece together the chain of events leading to these cataclysmic events. We will explore the enigmatic hypernovae, those ultra-energetic explosions that challenge our understanding of stellar physics. Join us as we embark on this cosmic quest to understand the awe-inspiring power of supernovae and hypernovae. Stars, those twinkling beacons in the night sky, are not eternal. They are born from collapsing clouds of gas and dust, ignite with nuclear fusion, and spend billions of years fusing hydrogen into helium. For stars much more massive than our Sun, the end is anything but peaceful. A supernova, a cosmic explosion of unimaginable power. In the next sections, we will delve into the two main types of supernova, Type 1 and Type 2. Type 1 supernovae occur in binary star systems, where a white dwarf siphons material from its companion star. When it surpasses a critical mass, a runaway nuclear reaction ignites, leading to a cataclysmic explosion. Type Ia supernovae are particularly interesting to astronomers for their consistent brightness, making them valuable tools for measuring cosmic distances. These explosions play a crucial role in enriching the interstellar medium with heavy elements. Type 2 supernovae mark the spectacular end of massive stars, those at least 8 times more massive than our Sun. As a massive star burns through its hydrogen fuel, it produces heavier elements, creating a layered structure with iron at the core. The core collapses, triggering a shockwave that blows the star apart in a brilliant supernova explosion. Type 2 supernovae are prolific producers of heavy elements, essential for life. Throughout history, astronomers have observed numerous supernovae, each leaving its own mark on the cosmic tapestry. One of the most famous supernovae occurred in 1054 AD, creating the Crab Nebula. Another notable supernova, SN 1987A, provided astronomers with an unprecedented opportunity to study a stellar explosion. Each explosion enriches the universe and shapes the galaxies we see today. Imagine a supernova, but amplified 1,000 times over. Enter the realm of hypernovae. These celestial events are so energetic they make supernovae look like mere firecrackers. Hypernovae occur when extremely massive stars, those exceeding 100 times the mass of our Sun, reach the end of their lives. These cosmic titans provide a glimpse into the most extreme environments in the universe. The formation of a hypernova is driven by the intense gravity and nuclear reactions within the core of a supermassive star. As these stellar giants exhaust their nuclear fuel, they face an inevitable fate: gravitational collapse. The iron core collapses, triggering a shockwave that rips through the star, resulting in a hypernova. The collapsing core forms a black hole, releasing powerful jets of energy observed as gamma-ray bursts. Hypernovae, though incredibly powerful, are also incredibly rare events. One such observation was SN 1998 BW, associated with a gamma-ray burst, providing strong evidence linking these two powerful phenomena. Another notable hypernova candidate is SEN 2006 GY, an exceptionally luminous supernova. These observations have provided crucial insights into the dynamics of hypernovae and their connection to other high-energy phenomena. Hypernovae are connected to gamma-ray bursts, the most luminous explosions in the universe. GRBs are thought to be produced by jets of material ejected during the collapse of a massive star into a black hole. These jets release immense amounts of gamma rays, the highest energy form of light. Studying GRBs associated with hypernovae helps us understand the life cycle of the most massive stars. In the realm of stellar explosions, supernova and hypernovae reign supreme, each a breathtaking spectacle of cosmic fury. Supernovae, already incredibly powerful events, are dwarfed by the sheer energy of hypernovae. Supernovae can result from the thermonuclear detonation of a white dwarf star or the core collapse of a massive star. Hypernovae are triggered by the collapse of extremely massive stars, often associated with gamma-ray bursts, highlighting the diversity of stellar death. The energy released in supernovae and hypernovae is almost impossible to comprehend. To put it in perspective, a single supernova can briefly outshine the combined light of billions of stars in its host galaxy. Now, imagine a hypernova, an explosion so powerful it makes a supernova look like a flicker of a candle. Hypernova release a mind-boggling amount of energy, equivalent to trillions upon trillions of nuclear bombs detonating simultaneously. This energy isn't just released in the form of light and heat. Supernovae and hypernovae unleash a torrent of high-energy particles, cosmic rays, that travel across the universe at nearly the speed of light. These cosmic rays, upon interacting with interstellar gas and dust, can trigger the formation of new stars and influence the evolution of galaxies. The energy released by these explosions also plays a crucial role in forging heavy elements, the building blocks of planets and life. The intense heat and pressure within these dying stars create a cosmic cauldron where elements heavier than iron, such as gold, silver, and uranium, are synthesized. These elements, scattered into the cosmos during the explosions, enrich the interstellar medium, seeding future generations of stars and planets. Supernovae and hypernovae leave behind more than just a fading glow. These cosmic cataclysms create fascinating objects, stellar remnants that provide clues about the stars that once existed. Supernovae can leave behind either a neutron star or a black hole. Neutron stars are incredibly dense objects. Black holes are regions where gravity is so strong that nothing can escape. Hypernovae are thought to leave behind only black holes. These black holes release powerful jets of energy. The remnants of supernovae and hypernovae continue to shape their surroundings. Neutron stars can emit beams of radiation. Black holes can distort space-time and influence nearby stars. Studying these remnants provides insights into the life cycle of stars and the evolution of the universe. Supernovae and hypernovae are not just spectacular celestial fireworks, they shape the universe we see today. These explosions enrich galaxies with heavy elements, driving star formation and galactic evolution. Imagine a galaxy without supernovae. It would lack the elements essential for life. Supernovae inject energy and elements into the interstellar medium, triggering new star formation. They are the engines of cosmic evolution. Understanding these explosions unravels the universe's mysteries. We often hear that we are all made of star stuff, and it's true. The very elements that make up our bodies, our planet, and everything around us were forged in the fiery hearts of stars, and those heavier than iron owe their existence to the incredible energies unleashed during supernova and hypernovae. Think of the periodic table as a cosmic cookbook, and stars are the master chefs. Stars spend their lives fusing hydrogen into helium, a process that releases energy and keeps them shining. But when massive stars run out of hydrogen, they start fusing heavier elements, creating a layered structure, like an onion with iron at the core. Iron, however, is the end of the line for stellar fusion. Fusing iron requires more energy than it releases, so when the core of a massive star becomes an iron core, it's a sign that the star's days are numbered. The core collapses, triggering a supernova or hypernova, and in those brief moments of unimaginable chaos, heavier elements like gold, silver, platinum, and uranium are created. These newly forged elements are then scattered across the cosmos in the explosions, enriching the interstellar medium with the ingredients needed for planets, life, and even the devices you're using to read this right now. Supernovae and hypernovae, though marking the end of a star's life, are also responsible for sparking new generations of stars. These explosions don't just scatter elements into space, they also send out powerful shockwaves that act like cosmic tsunamis, compressing gas and dust clouds in their wake. Imagine a calm pond, and then someone throws a rock into it. The ripples spread out, disturbing the water. Similarly, the shockwaves from supernovae and hypernovae disrupt the interstellar medium, creating regions of higher density within these giant clouds of gas and dust. These denser regions, under the relentless pull of gravity, begin to collapse in on themselves. As more and more material gets pulled in, the temperature and pressure at the center increase, eventually reaching the point where nuclear fusion ignites and a new star is born. In this way, supernovae and hypernovae act as cosmic gardeners, tilling the interstellar medium and planting the seeds for future generations of stars and their planetary systems. If supernovae and hypernovae are the gardeners of the cosmos, then they're also the architects, playing a crucial role in shaping the structure and evolution of galaxies over billions of years. Think of a galaxy as a giant cosmic ecosystem. Stars are born, live out their lives, and eventually die, often in spectacular explosions that release vast amounts of energy and matter back into the galaxy. This cycle of stellar birth and death, punctuated by supernovae and hypernovae, is what drives the evolution of galaxies. The energy released by supernovae and hypernovae can heat up the interstellar medium, regulating the rate at which new stars form. The shockwaves from these explosions can trigger star formation in some areas while disrupting it in others, shaping the distribution of stars within a galaxy. Furthermore, these explosions can drive galactic winds, powerful outflows of gas that can stretch for thousands of light years. These winds, like giant galactic chimneys, can expel gas and dust from a galaxy, affecting its chemical composition and influencing its ability to form new stars in the future. Supernovae and hypernovae are not just destructive forces, they're also essential regulators, participating in a delicate cosmic feedback loop that governs the evolution of galaxies and the universe as a whole. Imagine a thermostat that keeps a room at a comfortable temperature. When the room gets too cold, the thermostat turns on the heater. When it gets too hot, it turns on the air conditioner. Similarly, supernovae and hypernovae help regulate the conditions within galaxies, preventing them from either collapsing into themselves or expanding too quickly and losing the ability to form new stars. The energy released by these explosions can heat up the interstellar medium, increasing the pressure and counteracting the inward pull of gravity. This helps prevent galaxies from collapsing under their own weight. Conversely, the energy and matter ejected in these explosions can also push gas and dust away, regulating the amount of material available for star formation and preventing runaway starbursts that could deplete a galaxy's resources prematurely. This delicate balance between the forces of gravity and the energy released by supernovae and hypernovae is crucial for the long-term health and evolution of galaxies, ensuring that the cosmic cycle of stellar birth, life, and death can continue for billions of years. Long before telescopes, humans marveled at supernovae, new stars blazing into existence. In 1054 AD, Chinese astronomers recorded a supernova in Taurus, visible even during the day. This event birthed the Crab Nebula, still studied today. In 1572, Tycho Brahe observed another supernova, challenging the view of an unchanging sky. These supernovae provide valuable data for modern astronomers, revealing clues about the evolution of stars and galaxies. While supernovae and hypernovae might seem like distant events, occurring in the far reaches of the cosmos, their impact can be felt right here on Earth. The very atoms that make up our bodies, the air we breathe, and the ground we walk on were once forged in the fiery furnaces of these stellar explosions. Remember those heavy elements created in the final moments of a massive star's life? When a supernova or hypernova occurs, these elements are ejected into space, enriching the interstellar medium. Over time, this enriched material can become incorporated into new stars, planets, and even life itself. But the connection goes even deeper. Scientists have found evidence of past supernovae in Earth's geological record. For example, deposits of iron-60, a radioactive isotope produced in supernovae, have been found in deep-sea crusts, suggesting that our planet was showered by debris from a nearby supernova several million years ago. These findings highlight the intimate connection between our planet and the cosmos. The elements that make up our world, and indeed ourselves, were created in the hearts of dying stars, scattered across the galaxy in cataclysmic explosions, and eventually found their way to Earth, where they became the building blocks of life as we know it. Today, astronomers are equipped with an arsenal of sophisticated instruments, both on the ground and in space, that allow them to study supernovae and hypernovae in unprecedented detail, capturing their light across the electromagnetic spectrum, from radio waves to gamma rays. Giant telescopes, equipped with sensitive detectors, can observe the light from these explosions billions of light-years away, providing insights into the early universe. Space-based observatories, such as the Hubble Space Telescope and the Chandra X-ray Observatory, capture images and data that would be impossible to obtain from the ground, revealing the intricate structures of supernova remnants and the energetic processes at play. But it's not just about capturing light. Scientists are also using other messengers from these cosmic explosions to study them in new ways. Neutrinos, elusive subatomic particles produced in abundance during supernovae, can provide information about the core collapse process. Gravitational waves, ripples in space-time, can be generated by the most energetic hypernovae, offering a new window into these extreme events. As our observational capabilities continue to improve, we can expect even more exciting discoveries in the future. New telescopes, such as the James Webb Space Telescope and the Vera Rubin Observatory, will push the boundaries of astronomy, allowing us to peer deeper into the universe and witness supernova and hypernova with clarity and detail never before imagined. Supernovae and hypernovae are cosmic fireworks, marking the explosive deaths of stars. These events shape the universe, scattering the building blocks of planets and life. Imagine galaxies filled with stars, where supernovae erupt regularly. It's a cycle of stellar death and rebirth, a cosmic dance. We are children of the stars, our existence intertwined with these explosions. Supernovae regulate star formation and enrich the interstellar medium. They are the cosmic architects, ensuring the universe remains vibrant. Despite our progress, supernovae and hypernovae still hold many mysteries. Each new observation brings us closer, but the universe always has more surprises. These celestial phenomena push our understanding of physics to the limits, driving astronomers to continue their exploration. The study of supernovae and hypernovae is a testament to human curiosity. These celestial events reveal the cosmos's intricate workings. With each discovery and technological advance, we gain a deeper appreciation for the universe. The cosmos beckons us to continue our journey. Imagine observing supernovae in real time, unraveling the secrets of the early universe. This is the promise of astronomy, a journey without end, transcending generations, the story of our universe and our place within it.